Hi and welcome back. This is the third and last video for Chapter 2. Now, in the previous two videos, I talked about the microscopic view of how gases and, materials in general is viewed. We think of, temperature as being related to the average kinetic energy of the particles that make something up. And I also introduced the idea of, ideal gases and what happens when your gas is not ideal. For example, you can talk about it using the van der Waal equation. Also talked about the reality of particles inside a gas and the fact that they can't just travel from one point to another point in space and not worry about collisions. Those collisions are relevant, as we saw, in the van der Waal equation. Now, what I'd like to do today is to give you a very, I'm not going to say qualitative, partially qualitative, partially quantitative um, view as to the reality of things. So here's what I mean. Well, when you think of the atoms and molecules that make something up, we're not just talking about one or two or five or 10 or even 100. You're talking about Avogadro's numbers worth of particles. So remember, Avogadro's number looks like 6.022 times 10 to the 23rd. That's a lot of atoms, okay? So individually tracking 10 to the 23rd particles is not possible with our level of computing or technology. So what we do is we deal with everything on average. Kind of like when you measure the temperature of a room, you're measuring an average. You're not measuring the temperature at all places, okay? So what that means is that you're dealing with statistics. Now, I know statistics is everyone's favorite mathematics, and everyone just loves stats. And of course, that's a facetious statement. However, I would like to remind you of one or two simple things from statistics. For example, the idea of an average or a mean. Now, when you take the average of something, what you do is you add up all the values, and then you divide by the number that you have. Right? You could even do the averages of squares. Or the square mean. Okay, or better yet, the mean square. And here, you would add up the values squared and then divide by the number. But look, you're dealing with lots of numbers here, okay? And as you discovered in calculus, sums, which is what you do when you add things up, and integrals are very closely related to each other. Now, when you do full-blown statistics, what you do is you end up doing calculus. Typically, what we do is we say that you have what's called a probability distribution. Now, your probability distribution contains all the information about all of the particles that you're looking at. Okay? And it's a probability distribution because you can use it to talk about probabilities. Now, probabilities have some restrictions. For them to make sense to us, typically what we do is we say that they range anywhere from 0 to 100%. How likely is something to occur? It's not going to happen. It's definitely going to happen. Now, percentages aren't something that we really handle in physics or in mathematics. Usually, what we do is we talk about fractions instead. And in that particular case, 0 would be it's not going to happen, and 1 would be the same thing as 100%. So it's on a fractional scale where you can go from anywhere, basically from 1 to 100, with 0 being understood as entirely unlikely and not going to happen. So if you have, for example, a probability distribution, something that tells you all about everything that you want to know about your thing, and you could have any range of values all the way from minus infinity to infinity. What we do is we normalize this thing. We put a constant in front, and we find that constant such that when you do this integral, you get 1. If I were to look at all the possibilities of something happening from one point in space to another point in space, from infinity to minus infinity, 100% likely. Okay, so this is called normalization. Okay, so when you're actually doing real full-blown thermodynamics, you end up using things that look a lot like this quite a bit. Now, here is a good simple example of a probability distribution that everyone probably is familiar with. This is called a bell curve. Why? Because it looks like a bell. You'll see that this thing right here is centered right here at 0. Okay. And this actually has a technical name. This is called a Gaussian distribution. And it forms the basis behind much of statistics. Now, mathematically, it has the form of e to the minus some constant times x squared. Okay? Now, so if I were to take and put that in here, okay, and I were to normalize it, pulling a out because it's a constant, and set that equal to 1, then whatever I get here when I solve for a would be the normalization or the value of the constant that sits out in front that makes this work. And then you can ask statistical questions. For example, if I want to ask, what is the average value of my distribution? I would say, okay, probability distribution, what is the average value of x? And whatever I get here would be the mean of x. Okay, probability distribution. What is the average value of x squared? Well, whatever this is would be the mean square. It's very elegant. It works very nice. And, most of your time is spent trying to find whatever P of X is so that, you can do whatever it is you're trying to do with whatever data that you have. So that said, let's talk about the integral itself, this one right here. This particular integral right here is a special one because it shows up in statistics and in physics so much. And you will not see this done in Calc 1 or Calc 2 or Calc 3 because it's difficult to do. This is an incredibly difficult integral to do. Sometimes you have to appeal to more advanced mathematics like complex variables in order to do this, using what are called branch cuts. We're not going to do that. We're not going to do anything like that except to look it up, because it turns out that if you take this integral, it's pi over a. So whatever your little constant sitting out in front of here is, that ends up being what this is. Okay? Now, so that said, now let's talk about how this applies to thermodynamics. So the distribution that you see used a lot in thermodynamics, which takes into account potentially interactions and stuff like that, is something called the Maxwell-Boltzmann distribution. It has this nice curve like this. It almost looks like a bell curve. It's a little steeper over here and a little more slanted like that. We're going to talk about why it has that shape here in a little bit. But it turns out that if you look at what it is that makes particles move around from a velocity standpoint, we say that the thing that they have when they move is kinetic energy. So what I'd like to do is to think about a situation in which the only energy that we're having to deal with inside our gas is just kinetic energy. We're not dealing with collisions or anything like that. Each time you have a collision, you have to attach a term. That would be an energy term talking about the collision. We're not going to deal with any of that. So our energy here really is just kinetic energy, 1/2 mv squared. Now, I'd also like to consider the case of just simple one-dimensional motion. We're going to extend this to 3 dimensions. I'm going to talk about it, but I want to be very clear. You're not required to know this math. This is relatively complicated at the level of calculus that you're at. I'm just trying to argue out why it looks the way it does, so you understand, or at least you've seen it before. Okay. So anyway, James Clerk Maxwell and Ludwig Boltzmann came up with this particular distribution to describe the statistics of large numbers of particles in a gas. Now, each particle is going to have this kinetic energy, but we also know that there is a relationship between this and heat and temperature. Okay, so if you think about mathematical functions, right? So let's look at our probability distribution here. It looks like this. It's some constant times e to the minus a times x squared, right? So the thing is that mathematical functions like sine, cosine, tangent, e, and all these things, the argument that they have here is supposed to be unitless. But if you look, energy itself has units of joules. So what Maxwell and Boltzmann argued was that it's energy that describes the properties of all of the particles that are inside your system. And you can normalize it. You can get rid of its units by taking 1/2 mv squared and dividing it by k sub b times t. If you remember, 1/2 mv squared is equal to 3/2 kBt. They have the same units. So they called their probability distribution F. It's a function of v and not of position because it depends upon speeds. And again, we're just looking at one dimension. I'm going to call this along the x direction. We're going to ignore y and z for right now. And it would be some constant times e to the minus 1/2 mvx squared divided by k sub b times t. Now, this is a random distribution. This is what we want. This is statistically, these guys aren't interacting with each other, so they're not biasing anything. It's like a bell curve. And in this case, A would equal to m divided by 2 times k sub b times t. Now I'm going to box this because we're going to be coming back to this a number of times. So my distribution that tells me about the behavior of my gas particles looks like minus a times vx squared. It has the same functional form as our Gaussian distribution right here, which means that I know how to do the integral of it. It's just the square root of pi over a. So here, if I want to normalize, which is what I want to do, I want to normalize this from minus infinity to infinity such that it equals to 1. There's a 100% chance that I'm going to find, or my particle having a velocity of anywhere from minus infinity to plus infinity. Absolutely. Okay. Then what I need to do is I need to integrate this thing, set it equal to 1. And as a consequence, I can find out what my normalization constant is. So let's just do that. So minus infinity to infinity, a times e to the minus a vx squared dv x needs to equal to 1. I'm going to pull the a out. What's left when I do this integral is just the square root of pi over a. That's equal to 1. So if I were to solve for a, what my little normalization constant is, if I move this over to the right-hand side, it becomes the square root of a over pi. And now if I take and I plug in what a is, it ends up being m over 2 pi k sub b times t. Now, so in one dimension, the equation that describes the behavior of my particles looks like the square root of m over 2 pi k sub b times t times e to the minus 1 half mvx squared divided by k sub b times t. Now again, this is just one dimension. Again, we're going to look at 2 and 3 dimensions here in a little bit. But I would like to point out that, this is relatively complicated mathematically. Now, so what I'd like to do is to use this equation to look at the average kinetic energy along one dimension. So I would like to find a bunch of squares apparently. I would like to find the mean kinetic energy. Now, how do you find the mean of things? Well, statistics over here gives us a suggestion. The mean of something, if you have a probability distribution that describes its behavior, is just that something integrated against it. Okay? So, what I'd like to do is to integrate my kinetic energy against my probability distribution like this. I need to find out what this is. Now, this right here is my probability distribution. And I'm going to cut and paste that real quick. Get rid of this garbage here on the end. There we go. So this is what I need to integrate. Now, I want to remind you that this right here, this was the same thing as the square root of a over pi. Remember, the square root of a over pi was our normalization constant, and then we plugged in what a is. This is a, remember. Now, I'd like to go back to this form, just like to go back to the form of putting a up here. And it's just out of expedience. It makes the math easy. So I'd also like to remind you that kinetic energy is 1/2 mv squared. Okay, so really what I'm integrating here is this. 1/2 mv squared times this. And this is the square root of a over pi times e to the minus a vx squared dvx. This is what's being integrated. Oh, again, one-dimensional, just long x. Okay? So, this is a constant. This is a constant. Now, so what we're integrating here is this right here. And this is not easy. So you could potentially do, partial integration, basically. You don't want to do that here. There's a trick. There's a trick. And the trick is this. So let's pretend that you're integrating this. Will you agree with me that if I took this and I took the derivative with respect to a, that it would bring down a minus x squared right here? I'm going to put a minus outside to offset the minus here. So you can see you get the original back. So what that means is that this right here is really just this. And I know how to do this integral. That's just the square root of pi over a. So what I'm stuck here doing is taking the derivative of this. So I want to take minus the derivative of d by dA of the square root of pi over a. Square root of pi is the number. So I'm taking the derivative of this. I get a minus 1/2 times a to the minus 3/2. The minus times the minus kill each other off. I get a 1/2 times the square root of pi times a to the minus 3/2. Now I'm going to leave it like this because this right here is just what the integral is. My average kinetic energy is going to be 1/2 m square root of a over pi times this stuff right here, a 1/2, a square root of pi, and an a to the minus 3/2. Now I'd like to pull out everything but the a's and the pi's. That leaves me a 1/4 m sitting out in front. And now what I'm going to do is to express these things as fractional powers. So this right here, for example, would be a to the 1/2. And this right here would be pi to the minus 1/2. This right here is pi to the 1/2. And then we already have a to the minus 3/2. These are going to kill each other and make that 1. 1/2 minus 3/2 is equal to minus 1. So at the end of the day, this ends up being 1/4 m times a to the minus first power. Now what's a? It's this right here. So let's bring this down over here. So there's a. So what that means is along the x direction, and I'm just going to put an x down here to remind us that this is one-dimensional. I have a 1/4 and m, and now I have a to the minus 1/2, or the minus first power, which flips this. That would be 2 times k sub b t over m. Now watch. M's cancel. The 2 is going to kill one of the 2's down here off, making this a half. Now that's interesting. The average kinetic energy along one direction is 1/2 k sub bt. The equipartition theorem, though. If you remember, your total kinetic energy is what you get when you look at the kinetic energy in the x direction plus the kinetic energy in the y direction plus the kinetic energy in the z direction. And you can see that just by looking at this. V squared is Vx squared plus Vy squared plus Vz squared. Right? So it's a sum. 1/2 for each direction or degree of freedom. which means that my average kinetic energy overall, which you could write as 1/2 mv squared, is equal to a 1/2 kBt for each, or 3/2 k sub v t. And as you can see, this is exactly the same result that we got when we talked about the behavior of particles in a box that didn't interact with each other and pressure. This is from the first video for the chapter. Okay? Now, so the energy is partitioned off into different degrees of freedom. And that's what's meant by equipartition. Okay? Now, so I just wanted to show you this to show you how this works. Were you to take a full-fledged thermodynamics class, you would do this, and you would also see where the Maxwell-Boltzmann distribution really comes from. This is just arguing out the form. In truth, the Maxwell-Boltzmann distribution comes from assumptions about individual particle characteristics, and then extending that to a sum, then extending the sum to an integral. And it's relatively complicated. Okay? Now, that said, I'll see you next chapter.